So we've talked about these greenhouse gases, specifically looking at carbon dioxide and methane. We know where they come from now, but the question is what has been happening over time? Is this something we should be worried about? A lot of times people who maybe aren't too keen on climate change or don't really understand it may say, oh, well, it's something natural. It's going through a natural cycle. And that shouldn't be totally discredited because there is a natural cycle. And so that's what we're going to explore today. We're also going to take a look at some of the worst and best offenders of these greenhouse gases to kind of get an idea of what are some of the things that play into the amount of greenhouse gas that is released by an area. So let's first take a look at the trends of carbon dioxide over time. So in this graph, we see the amount of carbon dioxide measured in a unit called ppm. This is parts per million. Essentially, if you have 1 million molecules, this is how many of those molecules are carbon dioxide. Remember, there's not that much carbon dioxide in our atmosphere, but we don't need there to be that much. The amount we have has been quite enough to warm up our planet so that it's livable. So here we have carbon dioxide for the past 800,000 years, so quite a long time. And because of these 800,000 years, we've been able to determine kind of what is the carbon dioxide trend. Now the way we get these values isn't from humans. We haven't been measuring it for 800,000 years. Humans haven't even been around for 800,000 years. Instead, what we've done is we've taken ice cores. So maybe you've seen pictures of these. They're essentially a cylinder of ice literally taken from the Antarctic. And when water freezes to create ice, little air bubbles form. And those little air bubbles is the atmosphere. That's the air that was around when that ice formed. Now, kind of like with rocks, the ice forms in these various layers over time in Antarctica. So it's ice building on top of ice, building on top of ice. We're able to age the different parts of that ice core. And we can literally take an itty bitty needle and stab those air bubbles that's in that ice. And we can take out the gases in that air bubble and we can measure how much of these different gases we have in that air bubble. So all of this data that you see, all of this, those are all from those ice cores. And as you can see, there's totally natural variation in the amount of carbon dioxide there is. Sometimes we have a lot, sometimes we have a little. It just varies depending on what time of year it is. Or really, I should say, where we are in our climate cycle. But what's been concerning is that what's been happening recently. What's been happening recently isn't a natural cycle, and you can see that pretty easily. So take a look at year 0, and this wasn't really starting in year 0, it was actually starting sometime in the 50s, which we'll explain why in a little bit. Sorry for my distraction, I'm trying to plug my tablet in so I can show you guys something. But if you take a look at year 0, and really 2008, you can see that we're a lot higher than we've been before. Yeah, we're going up, but this is higher than anything in our recent past. And this is where the concern is. We're concerned of, well, if this is where we've been in the past and we're a lot higher than that, what does that mean? So I want to give you an idea. Remember, carbon dioxide is a greenhouse gas. Those greenhouse gases are what's going to warm Earth's temperature. Now this line that just popped up, this is the line of where ice ages are. And what I mean by that is that anytime carbon dioxide fell below this black line, that's typically when we were in an ice age. And every time carbon dioxide is above that line, that's when we're not in an ice age. So obviously, in today's day, we are above this line, we are not in an ice age. But the thing is that these two things are so different, right? If these going from 200 to 300 and around 250 is ice age or not ice age, what happens when we're in the 400s? What happens if we're at 600 or 800? No, we're not going to be in an ice age, but are we going to be like on fire? Like, that's what we're kind of concerned of, is what's the other extreme? What happens if we have too much carbon dioxide? We know if we don't have enough, we're in an ice age. What about if we have too much? Now, this is from 2008, so our values have gone up, so I expect you to know this number. Today, the amount of carbon dioxide in our atmosphere is about 409 parts per million. So you got 1 million molecules and 409 of them are carbon dioxide. If we look at our last peak was around 290, 295. Yeah, we're a lot higher than that, right? We're like 20, if I'm doing really quick math, like 30% higher today. So huge, huge differences. Now let's take a closer look. Now, a lot of the data from that graph was from ice cores. But in recent years, over the past 50, 60 years, we have been recording the amount of carbon dioxide in our atmosphere. We've been recording it at an observatory in Mauna Loa. If you're not familiar with Mauna Loa, it is on the Hawaiian Islands. And this is important because the Hawaiian Islands are in the middle of nowhere. It's not next to some big city. It's not next to a whole bunch of public transportation. It's not around power plants. It's pretty isolated from the rest of the world, meaning that the carbon dioxide levels it's measuring should actually be some of the lowest in the world because they're not being influenced by big industry and by fossil fuels. So we've been measuring the amount of carbon dioxide in our atmosphere, and the black line is the one we kind of want to focus on. The red line is the actual measurements that have been measured every single day. We'll talk about why they kind of have this zigzag pattern on our next slide. But for this slide, just focus on the red. And we can see that is increasing quite a bit. So if we look at present day, so here is our present day value. Oh goodness, sorry about that. Let's get this pen on. So here's our present day value. We're calling this 409. And when we started measuring data, we were at, we're just going to 319. I know it's not quite, that's a little bit lower than that, but just for easy math's sake. So from about 1958 to 2018, so that is, let me do some math. That is 60 years. And in 16 years, we increased by 90 parts per million. So this is what's happened in like your grandparents' lifetime. We've increased by 90 parts per million. So let's go back to that previous slide. So we want to take about a 90-degree difference. So let's do this peak, so this right here, and then we want to change that by 90 parts per million. So that would be around 210, which looks like that's about here. So we've done it in 60 years. And if we compare these 2 points, this is maybe 120,000 years ago, and we'll just say this is 100,000 years ago. It took 20,000 years to make that same difference in our natural history record. 20,000 years. But it's taken us 60. So yes, there is definitely natural cycles, but natural cycles are not explaining all of the differences that we're seeing. And that's really the key point. Yes, there might be something natural going on here, but no, it is not the only thing that's going on. So I'm going to zoom in one more bit. Remember, red is really what we're measuring like all the time, and black is kind of the average. And by average, it's essentially we're averaging these peaks and valleys. These peaks and valleys happen every single year. You could see that on the previous slide. And the reason it happens is actually because of our seasons. It happens exactly once a year. So I'm going to draw the Earth. And we're going to make this, super accurate, of course. So here's North America. And we're going into South America. Here's Europe. Here's Africa, here's Antarctica. There's like some countries in the Arctic up here. That's actually not that bad. So most of our land mass is actually in the northern hemisphere. And because most of our land mass is in the northern hemisphere, that means most of our trees and most of our plants are in the northern hemisphere. Now when it is springtime and summertime in the northern hemisphere, that is when we're going to see carbon dioxide levels go down. So carbon dioxide goes down in northern hemispheres spring and summer. Why? Because those plants are growing, those trees are growing, they're photosynthesizing, they're taking in that carbon dioxide from the atmosphere, they're processing it, they're turning it into sugars. But then fall comes and they lose their leaves. They're no longer photosynthesizing. And so carbon dioxide increases again. Now, the southern hemisphere is really not affecting this that much. There's not really that many plants in the southern hemisphere as compared to the northern hemisphere. So the northern hemisphere is controlling this trend. They're controlling how much carbon dioxide is in our atmosphere. So it gets really high. This is going to be fall and winter. And it's getting really low after our spring and summer. Now, if you actually compare these, so here's like this low point. This low point looks like it's actually coming like right at the beginning of fall, right? So we've accumulated all this photosynthesis and like pretty much at the last day of summer is our lowest point, and that's when it starts going up again. And it'll continue to rise and then it starts falling. So here's our biggest peak. It starts falling pretty much right at the beginning of spring. Spring starts and that carbon dioxide comes down because those trees are photosynthesizing a lot. So the big point here is northern hemisphere is ruling the world. When it's photosynthesizing in the spring and summer, carbon dioxide is coming down. And when there's no more leaves around, carbon dioxide is going up. Now, this is another natural cycle. This is affecting how much carbon dioxide is in our atmosphere every single day. But as you can see, it's not that much of a difference. I'm going to go back to this other graph. Yes, we have all these zigzags, but they're actually pretty small zigzags, right? This huge trend going up, much bigger than those zigzags. Now, with that, I want to add, honestly, we could deforest everything and it wouldn't be great. We lose a lot of habitat. But trees are making small differences to our environment. The biggest differences are coming from us. These little zigzags is what our trees are doing. So yeah, if we get rid of trees, the zigzags will be lower, but once they stop photosynthesizing, carbon dioxide goes up anyway. So they're actually not making that much of a difference. Now I know I sound like a horrible environmental teacher saying the trees don't matter. They totally matter for a lot of other reasons. But when it comes to climate change, they're not really making that big of a difference. The biggest difference would be addressing our fossil fuel use.